In the last video, I talked a lot about shock basics and what goes on inside of shocks and stuff like that. This video, I thought we'd expand it a little bit more. I'd talk about dyno graphs, show you how to read some dyno graphs, and what to look for when you're reading your dyno graph. So let's roll the intro and we'll talk about more about shocks. I've spent the last 30 plus years working on race cars, building race cars, and racing cars. And I'm here to help you better understand racing technology. In the last video, we were real basic on shocks. So this video, we're going to go a little bit more in depth. We're going to talk about hysteresis. We're going to talk about transmissibility. We're going to talk, and I'll show you how to read a dyno graph and the different parts on it and what to look for. And then we're going to talk about pistons and the different parts on pistons and what they do and how to adjust them. The first thing we're going to talk about is hysteresis. And the way I understand hysteresis, it's a hydraulic locking. And when fluid can't pass freely through the system or through the shock, or maybe sometimes parts expand and then parts contract if the walls of the piston body are real thin and it's not a good design shock, what will happen is there'll be a higher pressure in the shock closing section, like either the rebound as it's closing or the compression size as it's closing. There'll be a higher pressure than the opening side. A lot of times, if it's on the compression side, I've heard it described as pregnant belly syndrome, because it'll come down on the open and then it'll get real big and it'll snap close at the bottom. It's not a good thing. I don't like it because I think a rebound open and a rebound close should be real similar. We'll go through it when we make the diagrams of how that looks and what to look for. Another thing that I've found with some of the shocks is when you adjust your compression and your rebound in a lot of shocks, it's a needle valve. Some shocks have shims or have plates in them with orifice holes, and they'll have the clicks, and if the orifice holes for that bleed section to control the bleed is not big enough and it's not matched well to the shim stack, you'll get a lot of hysteresis also. Personally, I don't like adjusting like the compression or rebound shocks with a bleed disc. I like the needle and seat better. Öhlins has a needle and seat system. I like those systems a lot better on both sides. I think pretty much every shock company except for the Integra IDAs use a needle and seat in the rebound cycle. The IDAs use a cover plate with the bleed holes punched in them for the compression and the rebound side. And I'm not really hip on that, although I do like some things about the IDAs. I think they're really good shocks, but I don't like those bleed discs. Another thing I want to talk about is transmissibility. And now I have never heard of or talked to anyone in the dirt racing industry where this has ever come up, but I learned about it from that Formula One engineer, and he uses it. It's almost like a traction tuning mindset. It's more of a mindset thing than something you're going to put into practical application, but it gets you thinking about where a shock should be for compression and rebound. Think about transmissibility of a car going through a parking lot with speed bumps. If you go over a speed bump with your car at a very low speed. Tire and the wheel and the car will seem to go up and down at the same time, at the same rate. You'll go over and you'll feel the car go up and go down over the speed bump. But now, I don't recommend people try it to see what it feels like. But transmissibility, as you get faster and that shock gets adjusting in different ways, and the shims, the manufacturer of the shock starts figuring out what it needs for spring rate and to get traction. Transmissibility would be basically taking your car through a parking lot at 70 miles an hour and hitting a speed bump. Now you would think, because at first point when the car went up and over that speed bump, that the car would almost go to the moon when you're going 70 and you hit a speed bump. But in actuality, transmissibility says when you hit that speed bump, the tire will travel into the wheel well and compress because of speed, compress at a different rate than if you were to go slow over that speed bump. The wheel will actually go into the wheel well and your car will stay a little more level than if you were to go over that speed bump slow. And that's what I was explained to me as transmissibility, is the difference in wheel speed and car travel speed and how things affect over bumps. So far, I have not talked to anybody in the shock industry that really even talks about it or thinks about it, but that's always stuck in the back of my mind when I get tuning on shocks and I think about a wheel going over a bump. I've always kind of cut things down to the core of thinking when I'm trying to tune a shock or build a shock and readjust the shimming. It's like what's happening at low speed and what's happening at a higher speed with bumps and frequencies and stuff like that. So it's not something you're going to use every day, but if you understand the concept that it's there and you keep it in the back of your mind as you start thinking about your car, it might get kind of interesting. Third thing I want to talk about is pistons and their designs, and there's a ton of different stuff that you can do with pistons, and shock manufacturers are continually trying different things between 3-port, 2-port, 4-port pistons, the size of the cover plate. They call the cover plate because your piston will have free-flowing orifices through for the compression and the rebound side. And the bottom plate that you'll put up against the piston to seal that piston off from the top of the bottom plate is a cover plate shim. And then what you'll do is you'll have a sequence of smaller and smaller shims that'll create like a fan type of a stack deal. The hydraulic fluid will flow through that piston, hit the cover plate, and then the cover plate will need to flex a little bit to let that oil out of there. Well, the stiffer the cover plate and all those shims stacked on top of it is, the stiffer your compression or rebound valving is. The top shim on that stack they call the torque washer, and that can vary between different. Some shock manufacturers I've seen they use a standard size torque washer. I've always done the Olin system. In the Olin system, the torque washer can actually vary in diameters as well as thicknesses. So I've always played with that torque washer, and you can get different curves in the valving on what you want to do. That's a little bit higher end than this video, but to understand that there is a cover plate and there's other shims that provide a pressure and hold that fluid flow through there at a certain pressure to give you a stiffer or softer shock. And there's both a compression side, which is on the bottom, because when you push it in, the oil is going to flow back through there, and the compression stack is always on the bottom of the piston, and on the top is your rebound stack. So when you go to pull the piston out, oil is going to flow back up through. So your rebound stack is on the top of the piston and your compression stack is on the bottom. Third thing in a piston that is very important is what they call bleed. There will be a certain amount of bleed for every system. I think I've seen some systems that don't use a bleed system, but that's kind of strange. They run a very soft, like a cover plate. So it's almost like the bleed starts in the cover plate area. But most pistons manufacturers, at least the ones that I have been into, always use a bleed system. And there's two ways you can do bleed. Actually, there's 3 ways you can do kind of a bleed system. One is on the compression controller, and that'll be a needle and seat, usually someplace in like the remote reservoir or something like that. You can open up the bleed a little bit. The second way, there is 2 ways. It's on the piston. You can supply a bleed through there. And the one way on the piston is a hole drilled straight through the piston from the rebound of the compression side, which will allow oil to free flow through that piston. The other way you can provide bleed is through a bleed shim. And it is a shim the same size as a cover plate with a little slot milled in it that will align with your ports in your piston, and you can stack those up to adjust a bleed, or you can have a very thick bleed shim which will allow more oil, but then it will add pressure to your valve stack. So that's a tuning tool, how you decide, or how the piston manufacturer decides to go through that. But just to know that there are 2 ways on the piston to adjust bleed is through a cover plate or a bleed shim, or a direct connection through with a hole through the piston. And then you have your other way where you'd adjust the bleed. Basically, it's a bleed up by your base valve, or it's in your remote reservoir deal most of the time. It's a little needle and seat that'll go through, or a bleed disc that'll go through to bleed off the oil going into your canister. The IDAs have it right on the piston. That's what makes those, when you flip your adjuster back and forth on an IDA, all your metering between your compression and rebound side is done on the piston. There's bleed discs on there that you can turn. When you turn that dial on the IDA, you're turning a bleed disc to allow either more bleed or less bleed right through the piston. The IDA pistons are very thick compared to most places, because everything has to get incorporated into that piston. It's a very complex and technical piston, but just to know that there is bleed disc, and it can be done on the piston, but most of the time it's done, like if you twist it and you have an adjustable shock, it's done on the canister side or something like that. It's either a needle and seat, or it's a bleed disc on the canister area. So let's go over to the drawing board, and I'll make some diagrams about pistons and what the different parts are, and then we'll look at some dyno graphs and how to read them and what I look for when I start reading dyno graphs. Okay, let's first start off looking at pistons and the different types and some things about pistons. You have 2 different sides to the piston. You have a compression side and a rebound side. When you look at your shock, where the body's on top and your rod is on the bottom, your compression side is always on the bottom, because when you push the shock in, it's going to want to force oil from the top of the shock through those plates. So what will happen is actually this will be on the bottom of the piston, and your fluid will flow through here, and these are, let's say it's a 2-port piston, this will be the compression side and it'll be on the bottom of the piston. I probably should have drawn them the other way around, but it is what it is. Then if you flip a piston over, you can't have this oil flowing through the same track. So on a 2-port piston, your compression will be, let's say, on the sides, and the rebound will be on the top and the bottom, so that you have 2 independent systems for the oil to flow through on that piston. And then some pistons, like I said in the previous sessions, is that the oil can flow through either a bleed disc or it can flow through a orifice hole in the piston. If you're flowing through an orifice hole in the piston, it will usually be a little independent hole somewhere through here or something, not even close to the rebound. Sometimes it's in the rebound area, but it'll probably be actually separated between the compression and the rebound, be over here someplace maybe. And the oil flow will go through the piston independently of what you have for a valve stack in the compression or the rebound side. It just flows back and forth. These varies in different sizes, real big to real small. The bigger, of course, the more oil go through there. The other way you can do bleed in a piston, like I mentioned before, is a bleed disc. And this is basically what a bleed disc looks like. This will be the hole in the center where your shaft will go through, and this will bolt where your piston will bolt through. And this gets slid down on top of the piston, and it will allow oil to flow through these bleed slots through the stack here. And you can stack a bunch of these up to get more bleed. The problem with stacking more of these up is you put a thicker series of plates in there, and your compression can get thicker or stiffer with the slots in there. So you could bleed off more, but then as soon as it starts coming off a bleed, you'll get a really stiff valve stack the more of these you put in there. And these will vary by thickness and stuff like that. I've even experimented making the bleed area here bigger with a thinner shim. I've done all sorts of stuff to play around with it. Your typical valve stack, like I said in the other video, is basically like this. The bottom plate that will go right up against the piston, and these are the orifices, let's say, that will go through your piston and to the other side. So oil will flow through here and hit your cover plate, both sides, I guess. Oil will flow through here and hit your cover plate, and it'll want to fan that cover plate out. This is what they call a cover plate or seal plate, and that'll block off these orifices, or these your flow passages, completely from the bottom to the top, or top to bottom, whatever cycle you're in. And then you'll have a series of other plates on top of there, varying thicknesses and even diameters to give yourself a different valving curve. And then on the top, your nut that'll bolt everything to the piston shaft will be right up here. And the top washer of different thicknesses and different diameters oftentimes is your torque washer. And this is a tuning tool also on what kind of valve you want to put into that piston. So that's a basic piston type, and there's 3-port where you'd have or you'd have a similar piston, but instead of divided into these 2 ports here, you'd have a 3-port deal where it would be, 1, 2, 3, and of course, in order to fit the same amount of ports, or a different amount of ports into the same diameter piston, these ports could probably be a little bit bigger. The 3-port would be a little bit smaller ports, but you'd have 3 of them. And it all affects on how that fluid tries to hit and fan those pistons to give it a better flow rate, different valving. Also a piston called a digressive piston. These are all basic linear piston types. I haven't heard of too many people using digressive pistons anymore, but a digressive piston is a very large port, and it's usually designed to make your dyno graph kind of blow off. You'll put like a heavy cover plate in there, and your dyno graph, if you're looking at one like an electronic version, it'll blow off and your pressure will stay the same as you increase. That would be a digressive. On another, like a computerized dyno graph, which I don't use, your linear valve rate would look more like a straight line. If we're doing that for a blow off, it would be more of a straight line up in there, or even like a progressive design, your dyno graph would look something like that. And this would be basically your vertical axis here on your dyno graph. So 3 things to look for. This would be more like a linear. This would be a digressive. And this would be a progressive. I used to play around with it, and I've heard of people playing around with this, and maybe more now. I haven't done shocks really about a year or even a little better, but this, I think there's a lot of potential here in the progressive area to do something with shocks. That's very powerful. Okay, let's look at basics of a shock dyno graph. Now this is like a pencil graph or a pen graph. AccuForce sells a good dyno. I recommend Keith's dynos over there. I've used computer dynos. I don't like them for some aspects of them, and I've never really got the amount of information out of them that I wanted. Keith's dynos and the pencil graph dynos, once you get using them and you get understanding them and you get looking for what you want to look for in them, I think they're excellent. They're a lot lower cost than a computerized dyno, and for the average racer, a pen graph dyno is all you need. You're going to get a dyno graph from a pencil operated dyno, a pen operated dyno, similar to this. Think about it as a crankshaft going, because these are crank dynos. Like we had talked about with the speed and time video, I do another video on speed and time, and it operates on a crankshaft. This portion up here and this portion up here will be the slowest moving. You'll actually hit at this exact point, and at this exact point there will be a 0 movement. At some point here, the pen or the shaft will stop totally and change directions, and it'll be traveling in this way. Your compression open here, this is it stops and you start going and you start pushing your shaft in. That's compression open. At the middle of the crankshaft, you'll get your highest rate of speed. Let's say it's 1, 2, 3 inches per second. And that will be on your horizontal line right where it crosses the horizontal line. That'll be the fastest that piston, that shaft will travel for the, I guess, the duration of the cycle. That's the compression open. After it hits compression open, the piston will start to slow down to get to the 0 point down here. So this will be the compression closed area, and it'll be decelerating until it hits 0. Then it's going to start going in the other direction and go for a rebound. The shock shaft is going to start coming out now. So you're going to go through your rebound open, and it's going to accelerate and accelerate and accelerate. This will be the fastest portion of your rebound cycle, and then it'll start slowing down till you get your 0 point at the top, and that'll be the slowest point of the rebound cycle, and then the cycle starts again. You're going to see this then in either 1 inches per second, 2 inches per second, 3 inches per second. And as you get faster, most of the time with a linear piston, then you're going to see a line that will be something like this. Compression open, compression closed, rebound open, rebound closed. Let's say that is 1 inch per second. And then you crank that dyno up to 2 inches per second. What you're going to see is it'll start off at the same place, and it'll get higher, and then it'll start to close. And the same within the rebound side, where it'll start to open, it'll start to close, and that'll be 2 inches. And then you go up to 3 inches, and you'll be out here. With each faster time on a linear piston, all these lines will be the same spacing apart also, because it's linear. As you increase each inch, a pure linear shock, these lines will stay evenly spaced as it gets faster and faster. You know, your 1 inch here in rebound, your 2 inch here in rebound, and then you'll have a 3 inch in rebound, and so on. Usually these get up to around 10 inches a second or so. But that's what that is. Like I said, a linear shock, a pure linear shock, I should say. All these lines will be the same. I haven't seen in a very, very long time a purely linear shock. There's always a little variation. Whether it's going to be bleed or something else, there'll always be a little variation in the separation between the segments. Bleed is real interesting, and it's a real big tuning device in shocks. It's one of the largest, because your shock shaft, you think about it, 2 times every cycle, the shock shaft is going to come to a complete stop and then try to switch directions. It'll spend a lot of time at that 0 range. So bleed is usually measured between a 1 and 2 inch area. Sometimes we consider bleed. But a real big bleed shock, most of the time, will actually be real pointed at the top, where the flow of oil can come through there real easily. It's not entirely the story, but when the flow can go through the piston real easily, it will actually, right here, it will get like 0 pressure real fast. A small bleed shock with a small bleed plate or a small orifice or whatever it is, it won't allow the oil to pass through the piston at the top and the bottom cycle. So most of the time on a smaller bleed shock, you'll find a real rounded top and bottom. A big bleed shock will oftentimes show you a real pointed top and bottom. That's the difference between small bleed, and there's, like I said, it's all very more complicated than this. You can have a big bleed sometimes, or a bigger bleed and match your bleed, but then put heavier cover stacks so it'll appear a little bit different. But as that valve is starting to close there, that is very important. And how that bleed is released through there and released through the valve. That's because a lot of time your traction in shocks happens to be where the shock changes direction because you're going over bumps. So when the shock changes direction, it's real important to figure out what you want for bleed, and bleed is a huge tuning tool for shock people and people that get into it. Okay, the last thing I want to talk about here is hysteresis. And like I described before, it's kind of a hydraulic locking effect to what I understand. There's probably people that can describe it way better than I can and know it a lot better. But I understood it as a hydraulic locking in the shock. And there are shock manufacturers that just the design is poor and it produces a lot of hysteresis in them. But what happens and what to look for on a dyno graph is, our original diagram here of rebound close, rebound open, compression close, compression open is translated here. So this would be your compression open area, and a shock will start off, and then all of a sudden this is the fastest portion like we show on the crank, and all of a sudden it'll start slowing down. So you would think those valves would start closing and it would close at the same rate. But what happens is the hydraulic locking and how the oil gets through there, a lot of times it's the hose system, or the reason that they went to the piggyback is to eliminate a lot of the hysteresis. And how the adjuster is on the compression side a lot of times will provide a lot of hysteresis. But what it is, the shock will open as normally, and then right down here as the shock starts to close, it retains a lot of pressure. And what you get is the pressure retains, and then maybe as it slows down enough and you get into like a piston bleed area, it'll snap closed. So this is not good. I don't consider this good. Maybe some people don't worry about it, but I never liked this. I always liked a very open and closed area where they close about the same. And I always tried to get my shocks that I did so they would open and they'd accelerate and then they'd decelerate and they'd close. Because then you're using more of the springing effect of the shims and how it's all stacked up to provide your valving. Something like this, I believe, is to be much more consistent than dealing with something like this. This can get kind of crazy and it's not consistent. It probably leads to a lot of car fade from what I can think of. Of course, I've never done any experimenting, so I don't know. But just the way I run through it in my mind, this isn't good. Now, a lot of times, this is like usually like an old school, maybe a right rear, maybe even a right front, sometimes old school stuff. But now when we get into that right front stuff with the big rebound, we're tying those right fronts down. If they're, a lot of times you'll see them like this. And what happens is you'll hit a rebound cycle, and you'll get your rebound open, you get your rebound closed, and you'll start blocking off that bleed in that right front with the adjuster or something to get that right front, I guess, to tie down, and you'd get a real instant snapping. And this is hysteresis basically, because you're not allowing that shaft to close at the same rate it opens. I don't think this is as bad as on the compression side, because on the compression side you're going up the front side of the hill. But to tie the right front down and you want the ultimate compression with your right front, you don't want your tire locking when it goes over a bump, because then your traction will get tossed out of the right front. I always like the right front if you want to tie it down some, but it should be able to go up and down over bumps. It all has to do with weight transfer and roll centers and soft right fronts and everything, and weight transfer to keep the car on that right front without having to do it with a shock, because doing it with a shock will take traction out of the tire. Maybe the car will drive better because you're keeping it at attitude and you can still gain laps faster, but in a very technical state, if you're tuning your shocks for ultimate traction of the tire, this just doesn't make sense to me. A lot of people do it, a lot of people don't pay attention to it, don't care about it. As long as that right front gets locked down, they're fine with it. That's something to look for. Typical right front. This is another deal, probably like the right front where you're locking down. This has probably got a little bit more bleed because of it's a little bit more rounded here. As it starts to close, the bleed's a little bigger. If you do it all with bleed and the bleed is real small, it'll wait till the shock really slows down, then snaps closed. So it gets into that bleed range where everything can stop. Like I said, this is probably a little bit more bleed because of the angle on this, and this is probably a little bit less bleed because it snaps closed faster. If you like this video, subscribe to the channel. I would really appreciate it because that really helps me out with YouTube. And ring the bell for some notifications. Next time you get in YouTube and you're looking for racing videos, if I put one up, it'll give you a notification on that and say, hey, go watch this video. So if you liked what I got, subscribe, ring the bell, and we'll see you in the next video.